Welcome to This Explainer. Today, we're diving straight into the absolute engineering marvels behind robotic surgery. We'll be breaking down how these systems fundamentally upgrade the biological limits of the human body, using incredibly complex mechanics and software to pull off maneuvers that would, quite frankly, be literally impossible with just the naked eye and a bare human hand.
So let's kick things off with a pretty fascinating question about a universal human flaw. Think about the most skilled, highly trained surgeon on the planet. No matter how much they practice, right, they're still limited by their own biology.
Section 1. Beyond the human hand.
Here's the thing. Natural human hands instinctively oscillate. They vibrate at a frequency of roughly 6 to 12 hertz. Now that physiological tremor, totally fine when you're, tying your shoes or pouring your morning coffee, but it is a massive, dangerous hurdle when you're trying to operate on tiny, fragile blood vessels inside a patient.
To solve this, engineers gave the robot what is undoubtedly its true killer feature. The system uses a software control loop that constantly samples the surgeon's input at an incredibly high frequency. It actually identifies those specific 6 to 12 hertz tremor patterns and just mathematically subtracts them in real time. So by the time the robotic output actually moves, the tremor is completely gone. It creates a robotic arm that is quite literally steadier than any human hand could ever hope to be.
Section 2. Mastering degrees of freedom.
Okay, so this entire system relies on a core concept called telemanipulation. That simply means the surgeon is not physically holding the tools over the patient. They are entirely removed from the immediate physical space of the operating table.
The crucial takeaway here is that the surgeon operates from a dedicated, ergonomic console, resting their hands on control grips while looking into a high-definition monitor. Their digital commands are then beamed across the room to the patient-side robot. You see, in traditional laparoscopy, surgeons use these long tools that pivot right at the incision point, which means moving your hand left actually moves the tooltip right. It's totally counterintuitive. By completely digitizing this connection, engineers were able to eliminate those awkward pivot points entirely.
And by getting rid of those pivot points, they replace standard laparoscopic tools, which, let's be honest, basically act like a pair of long, rigid chopsticks, with a dynamic system that provides true rotation, flexion, and articulation. This is huge. It's the monumental difference between merely probing human anatomy from the outside and actively performing complex, natural maneuvers on the inside.
Just look at how brilliant the engineering of the endo-wrist instrument is. If you examine the mechanical tip, it's actually driven by these incredibly intricate Bowden wires. Those wires are meticulously designed to perfectly mimic and frankly enhance human dexterity right inside those tiny surgical incisions.
Think about this for a second. The endo-wrist actually provides 7 degrees of freedom. That physically exceeds the natural human wrist, which maxes out at 6. This artificial joint gives you 90 degrees of articulation, letting surgeons bend and twist in cramped little spaces where a human hand simply couldn't physically fit.
And that high degree of freedom is paired with another absolute digital superpower, motion scaling. This is the process of mapping a large, comfortable movement at the console, let's say a sweeping 5-centimeter hand movement, and digitally scaling it down to a highly precise 1-centimeter micro movement at the actual instrument tip. It literally grants the surgeon microscopic precision.
Section 3. The illusion of touch.
Now, there is a very common misconception out there among patients. A lot of people assume the surgeon can somehow feel the surgery through the robot. But actually, the DaVinci system completely severs that physical connection. The surgeon cannot physically feel the tissue they are cutting, suturing, or pulling.
When engineers were designing the system, they faced a really brutal trade-off. They obviously wanted to include tactile sensors to push force feedback directly into the surgeon's fingers. However, the sensors required to do that effectively were just way too bulky. Even worse, they were incredibly difficult to sterilize for the operating room, and they often totally lacked the necessary precision for delicate tissue. So, what do? They completely abandoned force feedback, choosing instead to go all in on absolute visual fidelity.
To compensate for that missing sense of touch, surgeons have to be trained in this wild sensory substitution technique called visual haptics. They have to watch the tissue super intently on their 3D monitors. They learn that if a membrane or tissue begins to turn white on the screen, they're pulling too hard. Their brain literally has to learn to use their eyes to gauge physical force. It's an incredible adaptation.
Section 4. Latency and motion scaling. Because you're relying entirely on sight to feel the surgery, we have to talk about the absolutely critical metric of latency.
In this system, latency is the split-second delay between the surgeon moving their hand at the master console and the robot actually responding visibly on the screen.
Researchers actually measured the photon-to-photon latency of the DaVinci S system, meaning the exact time light hits the camera until it emits from the surgeon's display, and they found an average delay of just 62 milliseconds. That is staggeringly fast, perfectly keeping the visual lag safely below the threshold of human perception.
And that sub-perception speed is strictly guarded for a reason. If engineers try to intercept that video feed and pass it through standard computer memory for extra processing, it easily tacks on over 100 milliseconds of latency. Delays of that size instantly destroy that vital illusion of touch. It causes perceptual desynchronization, reduces user performance, and most dangerously of all, directly increases surgical error rates.
Section 5. Built for safe failures.
Look, because a surgical robot is essentially critical infrastructure operating intimately inside a living human body, engineers couldn't just rely on standard software. They had to design multiple overlapping layers of intense hardware and software fail-safes.
Think about it. What if the power fails or a video signal drops mid-surgery? Well, the robotic arms do not drift. They don't drop, and they absolutely never move unpredictably. Instead, dedicated components acting as physical loss of signal switches trigger instantly. This cuts power in a specific way that rigidly locks the instruments safely in their exact current position, allowing the human surgical team to immediately step in.
Looking back at how brilliantly we've digitized and optimized human movement here, it leaves us with a truly provocative thought. Newer systems are already tracking performance metrics to provide intelligent feedback, and researchers are currently mapping these exact, precise surgical maneuvers to train artificial intelligence. As these robotic systems learn to automate specific subtasks on their own, how long until the robot no longer needs a human hand at the console at all? Definitely something to keep an eye on. Anyway, thank you so much for joining me for this explainer. I really hope it gave you a whole new appreciation for the mind-blowing engineering behind modern medicine.